So essentially now this is what the metric does for us. It gives us a way to essentially turn a vector into a one form and vice versa. So one way that you can view the metric is that it essentially now provides us an isomorphism, or just a way to essentially relate the vector space with the dual space. Because given the definition of a metric, we can now essentially just take any vector, plug it into the metric, and turn it into its corresponding one form. So let's just say a little bit more about this now, and this is going to be a very useful trick, or not a trick, but just a useful technique that we're going to use quite frequently. The way that we usually like to state this property is essentially that we use the metric to raise and lower indices. So we've already seen the index lowering property. So we usually like to state this in terms of indices and only indices on components, because essentially, as we saw, all of the action happens with the vector components getting turned into one form components. So we usually just kind of forget about the basis and just work with components when we write expressions like this down. It can be misleading at times, but at other times it can be helpful. So what we essentially say is that the metric components, when we contract metric components against now vector components, this contraction produces a new object, which are going to be the one form components associated with this vector v. And now this expression which I've written here is going to be, and so now the expression which I've written here, kind of writing in this way, ignoring the basis, this is how you'll often see physicists working with vectors and tensors. They just forget the basis completely and just talk about components. This is perfectly valid, but you kind of lose sight of really what's happening here. What's actually really happening here is that we're just multiplying a set of components just by some set of numbers. It's just turning it into another set of numbers. But what's important to realize is that now this kind of set of components is no longer attached to a 0,2 basis, it's just attached to a 0,1 basis, because essentially one of the bases has been effectively eaten up by one of our vector bases. So you need to be really careful to keep in your mind that all that's going on with these kind of index raising and lowering expressions is we're just multiplying numbers around, but we're just hiding the actual tensorial stuff that's going on, which is happening with these bases. But it's perfectly fine to just keep all of that hidden and just talk about components, as long as we always are clear and remember that upper and lower indices correspond to completely different objects. Well, the objects, the actual indices, they're just numbers, or the components rather are just numbers, but it's just they have to be attached to the right kind of basis vector. So the metric components can lower vector indices and turn vector components into one form components. And now similarly, we can use a very similar technique to turn one form indices into vector indices. So just as we have the metric components here, essentially we can just realize this G mu nu is just essentially it's a matrix, just an array where each of the G, say the 1, 2 component is just some number, and we can just arrange these components in an n by n matrix, G00, G01, and so on. And so we can represent the components just as an array or a matrix. We could consider taking the inverse of that matrix, and that's essentially now going to produce something which is effectively the inverse of this metric tensor, and we express it by essentially giving it upper indices. And now the way to kind of rigorously state how we form this inverse metric, as it's known, is that we essentially just write the rule that when you contract the metric components against the inverse metric components, this whole thing has to give you Kronecker delta. with the respective indices. And now essentially this is just a statement that the matrix of components representing the metric and the inverse metric, they're essentially just inverse matrices. So using the inverse metric, we can now take a set of one-form components, just give them a hat to make it explicitly clear that they're one-form components, and after we perform this contraction, we're just left with a set of vector components. So this is probably one of the key properties that the metric has, or it's you can essentially now take this as being the way in which we define a metric. Essentially this would have been true really for any tensor which I wrote down. If I just had some arbitrary tensor t mu nu and I contract it against a set of vector indices, well, after the contraction this is just going to be some object that just has a single lower index. But now it doesn't necessarily have to be the case that this v hat is the dual to this v. Essentially this is just a general statement of tensor contraction, but now the metric is special in that, well, essentially we choose the components, or the components are defined in such a way that essentially this is always true. That when we contract any vector with the metric, it's going to produce essentially the one form which is associated to that vector v. So this is all well and good. This is just kind of the machinery of what the metric does when we feed it vectors. Essentially it does something to the vector components to turn them into a one form. So how is this useful? Well, let's just consider what happens now if we plug in the same vector into the metric into both slots. So as we saw, I'll just write this kind of quickly now in components. As we had before, the metric components, the metric basis, one form, and now we plug in one copy, and then we want to plug in another copy. So remembering that whenever we introduce a new object, we have to give it a new kind of pair of indices to ensure we never have more than two of the same index, upper or lower. So all I've done here is just plugged in an expression for now the same vector v, just expressing it using a different index to stay consistent. So I'm plugging in the same vector into the metric now essentially twice. So as we've seen, what's going to happen is that the metric is going to turn one copy of that vector into a one form, and then that one form is then going to eat essentially the other vector that we plugged in. So let's just go through. So first of all, we have that this bracket does the contraction as we saw previously. We're just going to get a delta with a mu and a sigma index, and then when we sum over, this is just going to give us a delta mu sigma with then a v sigma. We just sum over everything, we're going to get a v mu. So we just have our v mu, our set of components, which then of course after the metric we sum over this index, we'd be simply left with the kind of one form version of that vector set of components. And now just the final part of the expression is still here, just this angled bracket. Just we can quickly realise, okay, it's going to give us a delta nu rho with a v rho. So it's just essentially a v nu. So the final part of the expression is now just v nu. So now we can see all that we have to do is sum over these v nu indices, and this whole thing is just going to amount to some real number. Now maybe to make it clear that this is always the same vector, I'll get rid of the hat on its one form components, and now you should hopefully recognise an expression like this as looking quite a lot like the dot product, which you've probably seen from kind of simple vector calculus. So what's actually happening here is that we're essentially just taking the vector So if I just start writing out this expression, it's going to be v0 plus v1, and so on. And essentially you can kind of view this as just effectively being the square of each of our vector components summed together, which does represent the dot product. If you remember when we defined the dot product of two vectors, say A dot B, if we had them as a list of components, say AI and BJ, we would express their dot product as you essentially just take the A0 component, you multiply it by the B0 component, and so on. So this is A0, B0, A1, B1, and so on. You could just concisely now write this expression as, well, to ensure that we're summing over the correct I equal to j indices, we include a Kronecker delta, and then we say AI bj. So this is just a way of writing down the dot product of just real R3 or Rn vectors. But now what I want you to realise, or we can first of all draw the connection between these two expressions, and we should realise that they are in fact a statement of the same thing. Essentially this expression here is just the general expression for how a vector eats a one form. In this case we're summing their components and we're just making sure that these components are always equal when we multiply them. So we're never going to have a v0 times a v1 component, for example. But what we should realise this expression, or another way that I could write this expression now, I could just rewrite one of these one forms using our metric. So all I've done is just take this expression, essentially now using the metric to rewrite this set of one form components using our vector components. And now looking at this expression, it kind of looks quite clear what's happening. We're taking the metric and we're just kind of feeding it two vectors, just by kind of juxtaposing them next to each other. It doesn't really make it very clear what's happening mathematically, but this expression is just this expression up here when we have the vector in both slots. But now what we should see is happening is that essentially all the metric is doing is it's turning this first set of components into this set of one form components, and we can then simply just use that one form to contract with this other vector here. And that's how all these calculations happen in practice. And now what we should realise is that the dot product is just simply an example of this more complicated or more general calculation. Simply we just have to make the identification that the metric components, in the case where we're dealing with this dot product, they're simply just the Kronecker delta matrix components. So if we realise now that this Kronecker delta, which I've written, is not just any Kronecker delta, it's now a metric, we can just realise, oh, well, what this metric's going to do, well, it's just going to lower this index here, and we're just going to get something like A, J, B, J. And now that's actually how the dot product is computed. Essentially using this simple metric, essentially just turns one of the components into one form components, while if we just multiply by the metric, it's just multiplying by the identity matrix. So in this really simple case, the one form components are going to be the same as the vector components. And now essentially you can just perform this sum of a lower and upper index, and it's going to give you the result, which is the dot product. And so the dot product is usually something that happens in R3 or Rn, and now we should realise that it's, or a better way of realising the dot product is to say, well, it's just simply the metric acting on a pair of vectors in our space. And it's this really simple metric, which is just essentially the identity matrix. But now, as we introduce a more general metric, these delta ij's could become any other matrix, g mu nu. And so when we contract vector indices against this non-identity matrix of components, the one-form components are going to be different to the vector components. But essentially the machinery of how this is calculated is always going to be the same. The goal is essentially going to be to use the metric to turn one of these vectors into a one form so that it can eat the other vector and just give us a real number. So now I just want to give a really, really quick way to kind of visually think about this. I introduced you in some previous videos about how we can think about these. Well, first of all, we can view vectors as being arrows. So this is just a vector in R3. We can view vectors as being arrows, or rather tangents to functions. But now we can view one forms as being sort of like normal surfaces. And then we can compute, essentially, if this is a one form, we can compute the action of that one form on the vector by sort of counting how many of these one-form surfaces are being pierced by that vector. That's just an intuitive picture, but now how I want you to view the action of a metric on a vector is essentially in a very similar way. What the metric is essentially doing is it's going to measure the length of a vector. So it's going to take any vector, it's then going to make a copy of that vector, but turn that copy into a one form, and then it's essentially just going to plug that first vector into the one form, and then that one form version of the vector is essentially just going to measure the length of that vector against itself almost, and that's essentially just going to result in a real number. And we can associate that real number with a length or a distance of this vector. And so of course the real number which we obtain here is going to depend on the metric or the geometry of the space in which this vector is living. So if you remember that the metric is essentially defining the geometry of our space, we can have vectors in R3, but then we can have various metrics that we can introduce on that R3. And now what this metric is doing is it's essentially just assigning a value to this kind of quantity which I'm pictorially representing here as just kind of the length of this vector. But now that length gets a concrete number value when we pick our metric components. And of course now that length is going to be determined essentially by the geometry. That's realised by essentially realising that this length is computed using the metric. Okay, so we'll just summarise everything which I talked about today. So we went over in much more detail this metric tensor object, which, as I said in previous videos, essentially defines the geometry by essentially now giving us the infinitesimal distance, which is defined between any 2 points. And now we saw how this is computed in practice using our kind of basis machinery that we have introduced for the one forms and vectors. And we see how these calculations are all fairly simple. They're all just essentially boiling down and using this definition. Essentially this definition comes in everywhere, and it is really useful for us in easily evaluating these kind of expressions. And so we've seen how these metric components are used, and essentially we realise their action on vectors is to turn that vector into a one form, and vice versa. We can turn one forms into vectors using the inverse metric. And now we've really started to see what is going on when this metric acts on vectors. The example of when we act on a vector, 2 copies of that same vector, as we saw here, it kind of turns one into a one form, and then it measures the other vector using that one form. And this is how we should view or really see how this metric is defining our geometry. It's going to be specifying the lengths of vectors in this way.